Hey everyone, in this video we're going to learn how to solve systems of two variable inequalities. Our first example, graph the solution set to each system of inequalities. Don't forget to label the solution set. Our system, x less than or equal to -3 and y is greater than x plus 3. So we'll graph x is less than or equal to -3 first. So that's going to be a vertical line at -3. We're going to graph that as a solid line because we have less than or equal to. So we have equality, so solid line, so we'll do that first. And then we need to shade in the solution set. So where are the points where x is less than or equal to -3? So to the left of the line, all the points would have an x value that is less than, and on the line, it would be equal to -3. So there's our solution set to x is less than or equal to -3. Y is greater than x plus 3. To graph that line, it has a slope of 1. A point on the line is the y-intercept, which is 0, 3. So we have 0, 3, slope of positive 1. So we plot points on the line. And we have strict inequality, just greater than. So we're going to connect the points with a dashed line. So there's our line. And now we need to figure out where to shade our solution set. So we're looking for where y is greater than x plus 3. So just reasoning that out, that's going to be any point above the line. That's going to have a y coordinate that's greater than x plus 3. On the line, the y coordinate would be exactly x plus 3. Now, if you're not sure about that reasoning, don't forget, we still have that ability to use a test point. Right? So if we wanted to use a test point, pick the origin. So is 0 greater than 0 plus 3? Is 0 greater than 3? It is not. So the origin should not be in our solution set, which it is not. And we'll label this y is greater than x plus 3. So a couple things to notice. We now have to label our inequalities because we're graphing more than one on a set of axes. And now we need to come up with a solution to the system of inequalities. And that solution is going to be where our shaded region overlaps. So the blue and the green overlap right here. So this is going to be what we label our solution set. So I like to put a big S in that area. Okay, you might put a bunch of little s's, but something to indicate that the area where the shading overlaps is our solution set. That's what we're looking for. And then they'll usually follow up with a question. Name a point in the solution set. Or is this point in the solution set of the system of inequalities? And we can answer that based off of our graph. So just a little bit of a definition. A system of linear inequalities consists of two or more linear inequalities that have the same variables. The solution set of a system of linear inequalities are all the ordered pairs that make all the inequalities in the system true. Okay, and in this case, there's going to be an infinite number of those ordered pairs if there's an overlapping in their solution sets, and the overlapping is a solution set to the system. And we can only find that graphically. That's important to note. We cannot find a solution to these systems algebraically because there's more than one. It'd be tough for us to do that. Next example, the system is y is greater than 1/3 x minus 1 and y is less than or equal to -x plus 2. So we'll start with the first line. So we have a slope of 1/3. The y-intercept is the point 0, -1. So we have a slope and we have a point. So 0, -1, slope of 1/3. That's the wrong way, that's -1/3. Positive 1/3 would be up 1 to the right 3, up 1 to the right 3, up 1 to the right 3, down 1 to the left 3, down 1 to the left 3, down 1 to the left 3. Now, how are we going to connect those points? We look at our inequality sign. It is greater than, so strict inequality. So we have a dashed line. So we'll connect that now. And now we need to figure out where we're going to shade our solution set. So we're looking for where y is greater than 1/3 x minus 1. Okay, so the y coordinate of the point is greater than 1/3 x minus 1 above the line. So we shade above the line. And again, if you don't understand that, pick the test point of the origin. Is 0 greater than 0 minus 1? Is 0 greater than -1? It is in fact. So the origin should be in our solution set, which it is based on our shading. And then we're going to graph the next line. Slope is -1. The y-intercept is the point 0, 2. So we have our slope, we have our y-intercept, or a point. So 0, 2, slope of -1. Go up 1 to the left 1 as well. And we're going to connect those points with a solid line. Less than or equal to, we have equality. So we have our solid line, and now we need to figure out where we are going to shade. And before I forget, just because I notice it now, let's make sure we label that first inequality in red. So now y is less than or equal to -x plus 2, so the y coordinate is less than -x plus 2 below the line. So we're going to shade here. So we have y is less than or equal to -x plus 2. And again, we can check the origin pretty easily here, 0, 0. So is 0 less than or equal to 0 plus 2? Is 0 less than or equal to 2? It is in fact. Origin should be part of the solution set, which it definitely is. So now, what is the solution to the system of inequalities? Well, it's where the blue and the red overlap. So we'll put a nice big S in this region. So any point in this region is a solution to the system of inequalities. So if you see below, state a point in the solution set. So let's pick that point there. So that would be the point -9, +2. And if you wanted to be really sure that the point you picked is in the solution set, you can plug this point into both of these inequalities, right? Is 2 greater than 1/3 times -9 minus 1. So 1/3 times -9 is -3, minus 1 is -4. Is 2 greater than -4? It is. And then you can do the same thing here. Is 2 less than or equal to -1 times -9, so +9 plus 2. So is 2 less than or equal to 11? It is. Okay, so that's how we can be even more sure that we graphed it correct and we identified the solution set correctly. Next up, 2x minus y is greater than or equal to -4, and y minus 3 is greater than 1/2 times x minus 4. Okay, so to graph this first line, which is in standard form, let's use the intercepts. So the x-intercept is when y is 0. So when y is 0, we'd have 2x minus 0 equals -4, 2x equals -4, x equals -2. And the y-intercept, when x is 0, so we have 2 times 0 minus y is, let's go equals when we're finding that, equals -4. So we have -y equals -4. That means y equals 4. Okay, so we'll plot those 2 points. So -2, 0, and 0, 1, 2, 3, 4. Now we have to decide how we're going to connect those 2 points. So we look at our inequality sign. It is greater than or equal to, so that tells me we're going to connect those points with a solid line. Let's just fix that a little bit. There we go. Okay, so now we need to figure out where we're going to shade the solution set to this inequality. So let's use a test point. So if we test 0, 0, so I'll stick with green for this test point just so we know what inequality we're plugging into. So the test point, so is 2 times 0 minus 0 greater than or equal to negative 4. So is 0 greater than or equal to negative 4? It is, in fact. So that means origin should be part of the solution set. Origin's here. So that means we're shading below the line. So there we have 2x minus y is greater than or equal to negative 4. And now we're graphing y minus 3 is greater than 1/2 times the quantity x minus 4. So this is a line in point slope form. So very quickly we should be able to identify the slope as 1/2 and a point on the line as 4, 3. So we plot the point 1, 2, 3, 4, 3, and a slope of 1/2. And we look at the inequality sign. It is greater than, so strict inequality. So that means we're connecting our points on the line with a dashed line. And where are the points? Where's y minus 3 greater than 1/2 times the quantity x minus 4? So that's going to be above the line. And that's, I'll label it here, y minus 3 is greater than 1/2 times x minus 4. And if we're not sure, again, test the origin. So is 0 minus 3, so is negative 3 greater than 0 minus 4 is negative 4 times 1/2 negative 2. So is negative 3 greater than negative 2? It is not. So the origin should not be in the solution set, which we can verify very quickly. So where's our solution set? Our solution set is where they overlap. So this region right up here. So the next question is the point negative 2, 0 in the solution set? So is that point right there in the solution set? Well, that's going to take a little bit of reasoning. So first, it's on the solid line for 2x minus y is greater than or equal to negative 4. So that means it is part of that solution set, part of the green solution set. But for y minus 3 is greater than 1/2 times x minus 4, that point is on the dashed line. Now, this allows us to talk about what the dashed line means. The dashed line means that all of these points on the line are not part of the solution set. Right? If we plugged any point on this line into the inequality, so for instance, negative 2, 0, if we plug that in, and I'll do that down here, so we'd have 0 minus 3 is greater than 1/2 times negative 2 minus 4. So we'd have negative 3 is greater than 1/2 times negative 6. So we'd have negative 3 is greater than negative 3, which is not true. So that means any point on this line is not part of the solution set of y minus 3 is greater than 1/2 times x minus 4. And remember, for a point to be part of the solution set, it has to make both inequalities true. So is that point in the solution set? The answer is no. Hey, and did we need to show this workout? No. What we should notice now going forward is if we have a point of intersection that's on a solid and a dashed line, or two dashed lines, then that's not going to be part of the solution set. Next system, y is greater than or equal to negative 3 over 4x plus 7, and y minus 4 is less than negative 3 over 4 times the quantity x plus 4. So our first line, slope, is negative 3 over 4, and a point on the line is the y-intercept, which is 0, 7. So 0, 7, slope of negative 3, 4, so down 3 to the right 4, down 3 to the right 4, and we can go up 3 to the left 4. Now, do we connect that with a solid or a dashed line? We look at our inequality sign. Greater than or equal to, we have equality, so we have a solid line connecting our points. and we are looking for where y is greater than or equal to negative 3/4 x plus 7. So that's going to be any point above the line. You can check that with a test point. So y is greater than or equal to negative 3/4 x plus 7. And the next inequality is in point-slope form. So we have a slope of negative 3/4, and a point on the line is negative 4, positive 4. So negative 1, 2, 3, 4, positive 1, 2, 3, 4. Slope of negative 3/4, so down 3 to the right 4, down 3 to the right 4, down 3 to the right 1, 2, 3, 4. And we can go up 3 to the left 4. Now, how are we going to connect our points? Well, we have strict inequality, less than. So I'm going to connect it with a dashed line. And where are the points so that y minus 4 is less than negative 3/4 times the quantity x plus 4? That's going to be below the line. So we have y minus 4 is less than negative 3/4 times x plus 4. So where is the solution set to this system of inequalities? Well, the two solution sets to the individual inequalities don't overlap. So what does that mean? That means that this system has no solution. There is no point that is going to make both of these inequalities true at the same time. All right, and we should have noticed that something like that could have happened because they have the same slope. Now, what else could have happened? Well, if the blue region was shaded above the line and the red region was shaded below the line, so if we switched the inequality signs, then they would have overlapped right in between the two parallel lines. Okay, so when we have parallel lines, we have to just make sure we graph the solution set separately and see where they overlap. Okay, don't always assume that's going to be no solution, because that's definitely not going to be the case. Write the system of inequalities represented by the graph below. So let's start with this first line. It doesn't have a nice y-intercept, so let's use the 2 points that are defined for us to write the line. So looking at the slope, it goes down 3 and to the right 2. So slope of negative 3/2, and one of the points on the line is the point 1, 4. So let's write this in point-slope form. So we have y minus 4. Not sure what the inequality sign is going to be yet. Negative 3/2, x minus 1. Now if we notice, the shading is above the line, so the y coordinates should be greater than those that are on the line. So it should be greater than or equal to, right? Solid line means we have equal to. And we can check very quickly that our inequality sign is correct by plugging in the origin. So 0 minus 4, so is negative 4, greater than or equal to. So then 0 minus 1, so negative 1 times negative 3/2 is 3/2. So is negative 4 greater than or equal to positive 3/2? No. So that means we have this correct, because the origin is not part of the solution set. The other line has a nice y-intercept, and the slope is up 2 to the right 3. So we have a slope of 2/3, and the point is 0, negative 4. So we can write this in slope-intercept form. So y is equal to or greater than, we're not sure yet, 2/3 x minus 4. Now they've shaded the points below the line, so that's where the y-coordinate of each point is going to be less than those on the line. And we have a dashed line, so we have strict inequality. So it's going to be less than, y is less than 2/3 x minus 4. And we can do the same thing with the origin to see. Is 0 less than 0? 2/3 times 0 is 0, minus 4. So is 0 less than negative 4? It is not, which it should be, because 0, 0 is not part of the solution set. So we're all good. Our signs are correct. Our lines are written well. Now one last example. where we have an inequality and a line, just to see what happens when we combine the two. So graphing the inequality first, y minus 1 is greater than or equal to 1/3 times the quantity x minus 1. We have a slope of 1/3, and a point on the line is 1, 1. So 1, 1, slope of 1/3, so up 1 to the right 3, up 1 to the right 3, and then down 1 to the left 3, down 1 to the left 3, down 1 to the left 3. Looking at our inequality sign, we have greater than or equal to, so solid line connecting our points. Let's just adjust that so it looks a little bit more correct through the points. There we go. And where are we going to shade our solution set? So where's y minus 1 greater than or equal to 1/3 times the quantity x minus 1? Well, all the points above the line have a y coordinate that's greater than those on the line. We'll label our inequality. And then we have y equals 6 minus x. So that's a line with a slope of -1 and a y-intercept of 0, 6. So 1, 2, 3, 4, 5, 6. Slope of -1. And that's just a line, so we're going to connect it with a line, connect all the points. And that's the line y equals 6 minus x. So how are we going to figure out the solution set if we have a line and an inequality? Right, all the previous examples we looked where the solution sets overlapped, and that's where we labeled the solution set. But here, we just have a line and a solution set. So remember, what's the whole point of a system? We're looking for points that make both or the three things true. So we need points that make this inequality true and also are on this line. Well, so essentially we're looking for the points on this line that are in the shaded region of this solution set. So where are those points? Well, this point on the line starts it, and then this point, and then this point, and then this point, and that point. So our solution set is just this part. Let's see how good I can graph it. Just this part of the line. And my line's not perfect. I'm trying to make sure to go over it nicely. Okay, so everything on this part of the line is our solution set. This is the solution set. So if you pick a point on this part of the line, it would make this inequality true. It is part of the solution set. Now this doesn't typically happen, but I like this example just because we can combine two things that we've been doing, inequalities and lines, and it makes us think a little bit more carefully about what a solution set to a system is. Okay, so a couple things to remember. Make sure you're labeling your inequalities because we have more than one on a set on a graph. Make sure you're checking your solution sets, right? Because we're looking for where the solution sets overlap. So it's going to be important that we graph each individual solution set correctly. Use a test point if you have to. And then if you want to check that your solution set's correct, pick a point in the solution set and plug it into each of the inequalities. It should make both of them true. And then the last thing was that point of intersection. If one of the lines, at least one of the lines, is dashed, that means any point on that line is not part of the solution set. So that point of intersection would not be part of the solution set either. So now nothing left but for you to do more examples on your own so that you feel comfortable and confident with the material.